Okay, so welcome to our continuation on the lecture, rather the session area number 3, which is on the numerical descriptive measures and central tendency. I'm really sorry that due to some personal commitment, I had to postpone the last week class. So we are meeting after a week. I'm sure that some of you may have forgotten what we have studied like 2 weeks ago. Don't worry, we'll take not more than 5-10 minutes and try to recall our part one of this lesson, which has an absolute connection to the part two, what we are going to learn today. One thing is on the nature of the data set. The second thing is we are bringing in more than one variable into the picture. We call it the x variable and y variable. And then we will try to find the relationship between the co-variability, co-movability. Whether when you see the increase or decrease in one particular variable, whether there's another similar movement or opposite movement can be observed in the second variable. So that picture will be discussed at the latter part of the day. As in we are continuing our discussion. Hopefully, we can continue the part 2 today, and we can wind up the lesson number 3. You all know that once we're done with it, we are completing the subject area, and we are moving into the fourth. One of the most interesting areas of the examiners these days, that is the probability. Probability, of course, we will spend not more than 1 to 2 days time. The ample number of questions to be discussed and tested. But then again, we have to really focus on the learning as well as the core areas to be questioned at the examination. So that hopefully after that we are coming to the 50th percentile of the 50 percentage of the syllabus area to be covered from the weightage point of view. There are a few interesting areas in the what do you call these areas such as the net present value, then IRR computations, and then building up indexes and all. So these areas are coming under a section called the applications of the statistics. So, couple of last lectures ago, I remember that we had to spend sometimes maybe 1 or 2 lectures on those areas. But nonetheless, this time I have decided to, limit and try to coverage more breadth in the syllabus than spending not more than 1 or 2 days in one particular area. So that is a bit of an introduction as to where we are and where we are heading. But there's an important announcement for you by the IBSL staff. I want to mention it at the beginning of also. Before the 15th of this month, IBSL staff has communicated me to remind you that you have to register for your examinations. I believe that there will be a formal announcement also via email, but just keep in mind before 15th, you have to go and get yourself registered for the examination. And there's another plan from our side, that is to expedite this lecture series a little bit faster and try to complete it maybe 3 to 4 weeks before the planned time. So of course I want to discuss with you, we'll have the discussion after the class on your comfortability as to whether we are going to have maybe 3 or 4 more classes in a weekday afternoon, or whether you're pretty much comfortable on extending maybe 2.5 hours to 3 hours of this one particular class. So depending on the nature of the subject, sometimes for a class like indexes or net present value, I may be able to comfortably finish in 3 hours time. But then again, even if we stick to our routine 2 hour classes, and then maybe we'll have 2 or 3 extra classes maybe on a Wednesday afternoon or a Thursday afternoon, so on and so forth. Still, from my point of view, I'm comfortable either way. Okay, so at the latter part of the class, we will have that finalization of your comfortability, and we'll try to organize 1 or 2, maybe 2 to 3 or 3 to 4 extra classes in the upcoming weeks. That is purely again from the IBSL point of view, based on their request to expedite the schedule a little bit faster and complete. We are all doing this in good faith to make you comfortable at the examination. I mean, we all know that the prevailing situation in the country is a bit volatile, and IBSL is trying their level best to plan and program their classes, programs, as well as the examinations. So we'll have to give some leeway to them and give them the maximum support to plan their semesters. So yeah, for a year they have to conduct these classes for 2 semesters, session 1 and session 2. So that let's try to stretch our schedules, personal commitments a little bit further and try to support them. Okay, so those are the announcements, the plans, and where we were. So let me quickly take you to our initial part of the lesson number 3, not spending more than 5 to 10 minutes, and to bring you up to speed as to what we have covered. Okay, and then we will get on with the lesson number 3, part number 2 on the central tendency and dispersion. Okay, so quickly covering up, we understood that there are, this lecture series itself is going into 2 areas. One is on the central tendency and measures of central tendency. And the second area is the dispersion and the measures of dispersion. So this is where we are at the yellow colored part, where we are learning and trying to understand what sort of distributions of these data sets is going to bring upon. I mean, when you move into the next areas of probability and then standard normal distribution, students, you will understand the total relationship between what we are learning on the data set and why we are trying to slowly bringing in this data set into one standard form, so that you can compare, so that you can do statistical inferences, come into conclusions, design certain things, design thresholds, design machines, computers. So all these things is coming into the play of normalizing the data set. So that is where we are heading at the 5th lesson. Okay. So important thing to highlight is that this, at the start of this, you might not understand really that why we are learning the dispersion, why we are learning the nature of a data set, but just keep a small note. This is having a deeper relationship into our next couple of lessons. So let me just cover up only the important areas. We understood that there are 3 basic central tendency indicators named mode, median, and mean. Mode is the most frequently occurring number, median is the midpoint, mean is the average, rather than arithmetic average. So that once we discuss the relative advantages, disadvantages of different 3 indicators, especially, categorically looking at whether we're looking at quantitative data, whether we're looking at some comparisons, numerical aspects only. What if there's an outlier? Still look at these examples, 2, 3, 4, and 5, and then when you put up 1020, your entire distribution is going to get distorted for mean. But some indicators like mode or median may not really having impact. And last week at the Q&A session, week before at the Q&A session, you may recall that some of these things that we are learning as the where these are good measures and what are the advantages and disadvantages are being frequently tested in a good 2-mark or maybe a 5-mark question. Then we came into the area of dispersion, and we covered the first 2 in the part number 1. That is a range, mean deviation, variance, and standard deviation. We're continuing the discussion on variance and standard deviation and bringing up more variables today. That is what we are doing. Range is nothing but the smallest and the largest. Still, it's a useful indicator so that one can get an understanding what is the minimum and the maximum, what sort of a range is being spread around. Mean deviation is nothing but we take the average first of all, and then we compute the length or the distance between one individual value to that particular average. So why we take important is to straight line the modulus value. Why do we take it is to avoid this negativity. We did a computation week before, and we understood that if we did not take the modulus value, if we did not take the positive values on the students, what will happen? The mean deviation is going to be 0. Rather, once you take the plus numbers only, look at this example. Once you take the plus numbers only, you can comfortably calculate a mean deviation. And then you can come to a judgment. Look at this mean of 5 and then 1.9 and negative 1.9 is a mean deviation. I mean, just if you earmarked it, you can see majority of the data set is coming to cover in that particular one mean deviation area. Maybe if you put two mean deviations, the entire data set will be covered. Likewise, you can come into conclusion. So mean deviation is one of the very introductory deviation measures that we can calculate to get an understanding of how dispersed the data from the middle point, Okay. Then we moved into variance and standard deviation, and I really recall that I mentioned that this is the starting point of all the deeper calculations. Variance and standard deviation is like a brother and sister. I mean, nothing much to be deviated from one another. Once you calculate one indicator called variance, you just take the square root, and that is what we call as a standard deviation. And then we discuss importantly, once you square a particular value, that is going to go into a next stage. If you take 2s, 4s, and 3s, that is on one particular plane, and if you take the square values, 4s, 9s, and 16s, that it will be on a different plane of discussion. So that's why eventually we take the standard deviation and eventually elaborate the nature of the data set using the standard deviation. But we start the calculation with the variance. So variance is denoted as a S square and standard deviation as S or rho square or rho, based on whether we are looking at the population or the sample. Only thing to quickly recall is that whether you're looking at not this group to one group, whether you're looking at a sample or population is the salient take-home point. Look at these two equations, students, quickly. You have the I minus x bar. Now this part is not new. We learned this under mean deviation also. We take the square so that we don't really have to take the modulus value. Only difference, the salient difference is that for population, you take in capital N, see 500. But when you take the sample, instead of 25, you take 24, N minus 1. That is the only difference when you can when you try to calculate the variance and the standard deviation. For population and for sample. Okay. Variance and standard deviation, we don't have to discuss that again. Just that you take the square root of the variance, that comes the standard deviation. We discussed some questions. Practically how you do this for a given data set. I share this answer with you. Eventually, I invited you to try out your calculators also. Then that you can cross-check your answer at the exam. Don't ever try to learn the data mode of this calculator and quickly plug the answer. But eventually at the exam, you should demonstrate the fact that you know the theoretical part behind the calculation of the standard deviation. Okay. And then, yeah, we stopped our discussion here by introducing this coefficient of variation. Why do we really need this? Is simply because of we need to compare. We need to compare and come into decisions. When you have data sets with different units and significantly different means, then if you really do a comparison based on the absolute data, you can come into wrong conclusions. So that's why we take the relativeness. It's a percentage, the relativeness of taking the fraction of standard deviation divided by that particular population's x bar or the average, so that you can comfortably calculate this coefficient of variation. And I'm sure that you can recall that we discussed plenty of exam questions asking for different comparisons. So you have a factory, let's say you have 2 or 3 different types of bulbs, maybe 5 watt, 7 watt, and 10 watt. And then you have a given data set. You need to calculate which wattage bulb is having the significant deviation or a least deviation. Likewise, then you can easily compute this coefficient of variation, and depending on the number, whether you're looking at a larger number, smaller number, or a smallest number, Likewise, you can compare the data sets. There's no definite answer for a coefficient of variation like any Likert scale of, let's say, -1 to 0 to +1, and say whether it's a significantly deviating or significantly variation one. No, not like that. We use the coefficient of variation purely for the purpose of comparing two or more data sets distributions. Okay. So with that, yeah, I think we discussed this class example also. I really want to show you guys that, a good case of, let's say you have 1, 2s and 3s, 100 and 100 and 200 and 3. If you really look into the standard deviation, it is 1. But when you calculate the coefficient of variation, you can comfortably see that one data set, that is this 1 to 3 data set, is going to have a significant variation. 2 to 1, it's a 50% deviation. 2 to 3, 50%. But look into the 100, 200, 3 and 101 is just 1%, nearly 1% kind of a deviation. So that despite the fact that you get a same sample standard deviation, you can't really say that these distributions are having a less variability or more variability. You have to calculate the coefficient of variation also to get the final wording. Again, there's another data set which is on total two different scales, the 10,000s versus point decimals. There, what we observed is that you can calculate the standard deviation, as a two different measures. Look at these two numbers of 0.16 and 638. But then again, when you calculate the coefficient of variation, you can see, okay, but these data set seems to be varying hand in hand. The variability is pretty much like with like. So this is a few price example. So one can argue, okay, fine. These both countries seems to be importing from the same source, so their cost structure seems to be the same. Likewise, you can come to a conclusion. Okay, so that is where we stopped at the class number 1 for the first part, and then we discussed this ample number of questions, which we learn a lot of aspects of the examiner's preferences of testing, as well as some interesting knowledge. Okay. With that, students, let me introduce the second part on the lecture series on the this particular central tendency and dispersion. Why we are coming into this place again, I'm recalling, now we learn that we can represent the data set by maybe 1, 2 or couple of indicators like mean, median and mode. But that is not really sufficient. Why? We don't really know how deviated or how distributed these data sets are. So that's why we are bringing in more areas of variability. We are learning standard deviation and variance merely because of that. Now, we can't really stop it over there. We really need to understand that whether we are looking at these data are being scattered to one particular central point, scattered to the negative side, scattered to the positive side. Likewise, we need to understand the nature or the graphical representation of this data set in order to understand where the data is concentrated. So with that intention, we are going to learn these couple of indicators. The first two indicators are if I name them, skewness and curtices, to understand the graphical elaboration of the data set that we can discuss. And lastly, latter part of the lecture, we will learn the covariability of two or more variables, where we are bringing in more than one variable now into the picture. Up until here, even when we discuss the skewness and curtices, we are discussing on one particular x variable and its frequency. One particular x variable and its frequency. But over here, with the covariability introduction, you are learning two variables, x and y, p and q, a and b, coming into picture, where we are going to discuss how those things are going to vary from one another, whether we can find relationships and how strong those relationships is going to be. Okay. With that introduction, let's try to learn the first part, that is a skewness. Okay. So before we are coming here, in fact, there's a small missing piece in this lecture series. I really appreciate that if I get an opportunity to give you an introduction to a normal distribution, it will be pretty much perfect to discuss the skewness of the normal distribution. So pardon me, I mean, due to the nature of the lecture series, pardon me, let me give you the introduction here and then we will move on to the skewness. Okay. Now, students, casually, if you look into a data set like 2, 3, 5, 6, 6, 7, 7, 7, 8, and 9, likewise, when you see this data set, we could recall that from stem and leaf diagrams to the grouping, what we have eventually tried to see is to give a visual picture to the audience. Give a visual picture to the audience, a quick picture, one snapshot, so that anyone can understand, okay, whether this data set is being centralized to some point, what's the most frequently occurring number, what's the range, what's the minimum, maximum. Likewise, if you can put up some sort of a chart or a graph, then one can easily understand. So, importantly, remember, still we are looking at one x variable. Okay. What you call by this normal distribution is nothing but now you plot the frequency of this particular data. What I have done here, this is 2, this is 3, the height is 1, this is 1, and I can see, okay, hold on, this is 5, and this is 6. Why I have drawn this 6 a bit taller is because that I can see the frequency of 6 is 2. And about 7, I have drawn even higher. 8, again 1, 9, again 1. So once I do a simple bar chart like this, and if I try to join these bars using a best fitting curve, this is, yes, correct, this is sort of like a bell-shaped curve. In nature, students, in nature, when you plot this data of students' heights, exam marks, speeds, anything for that matter, from biology to even art, when you plot a series of numbers into that frequency, we eventually can come up with this bell-shaped curve. Bell-shaped curve. It's a curve. So something like this is a good example. Something like this is another example. So this curve can have many different forms. It can sometimes be very high like this. Sometimes it can be a very flat curve. Sometimes there may be not a pattern, but there may be one or two concentrations. Likewise, in nature, once you plot this standard data set into a small frequency distribution, you can find different shapes, but eventually all are forming up a small bell, be that bell. And by looking at the height and the location of that bell, we can come into different conclusions as to how this data is being dispersed. Okay. So that this bell-shaped curve later on we will be discussing as a standard normal distribution. Standard normal distribution. So did we have more than one variable up until now? Not yet. So if this particular axis is x, what is this particular axis? Y. This is going to be the frequency. Frequency. Okay. Not that x and y are two variables. No, this is x and this is not y. This is the frequency of x. X as frequency. Okay, that's enough for you to get an introduction to this plotting of this data set into a distribution. Okay. So that the word skewness is going to teach you uh, compared to a balanced symmetrical shape, whether we can identify that the data set that we are looking at is having a positive or a negative movement. Let me repeat that. In compared with a in compared with a symmetrical shape, in compared with a symmetrical shape, the data set that we are looking at, if it is also symmetrical shape, okay, fine, perfectly fine. We have a name for that also. But if at all, if it is been deviating even the slightest, this is the perfect symmetrical shape. And if this is what we are looking at in the blue color, now this is the instance that we are going to discuss under the skewness. Okay. So students, the skewness is nothing but whether a distribution is apart from the symmetricalness. Depending on the nature of the movement, we have identified two possible such deviations. One is called the positively skewed distribution, and the second one is called the negatively skewed distribution. Why would I discuss about the third one? Third one is not a skewness. It is the perfect alignment of the data set to a normal distribution or a perfect symmetrical bell-shaped curve. Perfectly symmetrical bell-shaped curve. Okay. We look into these instances detail carefully and try to learn their characteristics. The first one is a positively skewed distribution. Positively skewed distribution. I'm taking it through the text. If a smooth frequency curve of distribution falls with a longer tail, this is tail, longer tail towards the right side of its maximum point, this point, then such distribution is called right skewed or positively skewed distribution. Okay. In the distribution, students, in the skewness, typically we are discussing about the tail, longer tail. I mean, obviously now you can guess, okay, the negatively skewed distribution should be the opposite side, and which is perfectly correct. If the tail goes to the other side, towards the left-hand side from the peak, then such distributions is going to be the negatively skewed distribution. What are these trends we have indicated here? What are these trends? Mode, median, and mean. Now, these trends are the ones that we have learned previously, isn't that so? So, you can understand that all what we can conclude at this point is that we know once you plot a small frequency distribution, once you plot a small frequency distribution, like you put your x values into the x-axis and then such frequencies into the y-axis. X is here, y is here. And eventually, now look at this small distribution. Number 7 is the place where you can see the maximum number of concentrations is being noted, or the frequencies is being noted. In such instances, we call this as the what? Mode. We call this as the mode. So that's why, students, in this distribution also, you see the maximum height point is easily you can denote as the mode. You can denote as the mode. Let me take a little detour and skip the negatively skewed distributions also and discuss this symmetric distribution first. Now, here, students, what can we observe? Mean, median, and mode, all these indicators you can see are being aligned. Okay, so they are not aparting from one another. For instance, if you put some let's say fictional data like 2s, 3s, and 4s, and 5s, 6, 7, and 8 for discussion sake. Now, this particular value 5 is going to be equal to mean, median, and mode. This is maximum point. So easily you can take mode out of discussion. We can understand that it is going to be the case. But how did I derive mean and median is also going to be aligned? Because of the fact that in a symmetrical distribution, students, we can find symmetry. This part is perfectly equal to this particular part. There's 50% of data in the left hand side and another 50% of the data is on the right hand side. Symmetrical. You can fold this. If you draw this in a piece of paper, and if you fold it, these lines, these two lines are going to fall in one over the other. And from there, we can conclude, okay, fine. If that is the case, that is going to be the 50th percent point. So that's why I can take out this argument also, saying, okay, fine, median is also going to be now in the same place. What about mean? Now, what do you call by the mean? Mean is nothing but you take the entire values sigma, the summation, and divide by the number of items. So you have 2s, 3s, 4s, 5s like this, and you can see a symmetry nature also. If you add this set of numbers and divide by 7, you are going to get 5. Why? Because of the fact that the average is going to be the representer, or you're dividing by the number of items, as in you are computing again to the midpoint based on the weight, not based on the position, based on the weight. Based on the weight. So eventually, students, you can understand, okay, fine, mean is also going to be at the central point in that case. So before we discuss the positively skewed or negatively skewed distribution, I really want to show you, okay, fine, in a symmetrical distribution, data points are neither skewed towards left nor to the right. Data points are centralized. So that mean, median, and mode will take the equal values and will be located at the one central place. That's a symmetrical distribution. Okay. With that in mind, now let me take you to the positively skewed distribution. Now, what has happened? Previously, students, if you could recall, okay, we were jolly well discussing a distribution like this, where you could understand, okay, fine, mean, mode, median, all are at the same particular place. But now what has happened? You can see that, okay, the data set is being pushed towards one side. Or rather, you can see a longer tail in this particular data set. Is the tail on the right hand side is equal to the tail on the right hand side? No, it's not the case right now. So once you see the tail of the data set is moving, is having a longer or a shorter compared to the other side, there the skewness is going to occur. Why is this? It's simply because of the fact that, okay, the data is not located in a central way. It's been moved into one particular area. It's been skewed. The technical term is skewed. The data has been skewed towards one particular end. So I argued with you at the beginning, okay, in nature, once you plot the data set of a single variable into any distribution like a bar chart or a line chart, anything, you will find this nice bell-shaped curve. But seldom you can find these skewed curves also. Correct the fact that they also represent some characteristics of a normal distribution. You can still find an equation for this curve. You can predict the next value. All those characteristics are fine. But then again, there's one particular nature. The data set is being moved to one particular area. There's one famous or popular example which I quote always. The chemistry marks of a advanced level mathematics students, when once you plot the chemistry scores, that will have the impact of this positively skewed distribution. Why is that? Simply because of the fact that they are, I mean, the mathematics students are not very good at chemistry, so that's the norm. But the norm, it's not a rule, rather, it's a norm. So that those students will typically tend to score values like 40s and 50s to the chemistry paper. And compared to the physics or compared to the mathematics paper, those students' distribution on the chemistry marks will have a somewhat a lower averages, somewhat lower averages. So, uh, so once you plot that data set, you can always find a positively skewed distributions. So likewise, I mean, or despite the fact that we expect them to have the standard normal distribution or the symmetrical distribution, uh, once you look into the real data, sometimes depending on various other factors like this assumption of that chemistry is going to be a bit difficult for the mathematics stream students. Now the actual scoring is going to be coming into this skewed distribution nature. There are, okay, not spending much time, there are a few important salient points to highlight. One is the fact that where are we going to, sorry, locate the, now mode is fine. Why do I say mode is fine always? It's simply because of the maximum height point. So there's absolutely nothing but to discuss here, nothing but to worry. Nothing much to worry. Simply you take the peak point and demarcate mode, and this is done from our discussion. But what about the median and mean? It's very easy to remember in this instance, students. Why? Median is going to be always in the middle point from the mode and mean. Even if I quickly take you to the next graph, look for a minute, median is at the middle point. Mode is the maximum point and median is the second point. Here also, mode is the maximum point and median is the second point. And depending on the positively skewed or negatively skewed nature, you can find mean towards the tail. Why? Because the 50% is going to be equal to this 50% from weighted point of view. Weighted point of view. If I really try to draw this red line in the mode over here, what is going to happen? No. Then this is, I mean, this area may be something like 40%, and this area will be something like 60%. Yeah. So is that the point we are going to demarcate as mean? No. Mean has to be the 50th point. The point where from weight point of view, you can identify 50% of the data is towards the left hand side of the mean and 50% towards the right hand side of the mean. Now is it symmetrical anymore? Can you fold it and try to find the symmetricalness? No. So that's why we call it a skewed nature data set. Skewed nature data set. Okay. So I told you the easy way to remember on the nature of the mode, median, and mode mean. You start with mode always. The maximum height point in this normal distribution is your mode, no brainer. And median is also always going to be in the middle value. So depending on whether you're looking at the longer tail towards the right hand side, right skew or positively skewed, your mean is also going into that particular side. Okay. With that, we don't have to spend not more than a couple of minutes to discuss the negative skewed distributions. This is perfectly the other side. If a smooth frequency curve falls with a longer tail towards, see, again, I'm discussing about the tail, longer tail towards the left side from its maximum point. Such distribution is called the left skewed or negatively skewed. What is the previous one? Right skewed or positively skewed. This one, left skewed or negatively skewed. So here also, you can see the same observation. Mode as the maximum point, median the middle point, and mean is where this is going to demarcate for 50th percentage from the weight point of view, weightage point of view. Okay, we don't have to discuss this one on the symmetrical distribution. So quickly recapping, positively skewed distribution, negatively skewed distribution, or normal distribution is what we can observe from the graphical point of view when you try to plot the single variable data and try to understand where the data is being concentrated or cluttered. Okay. If you see a longer tail towards the right hand side, we call it a positive. If you say a longer tail to the left hand side, we call it a negatively skewed distribution. Symmetrical distribution is where you can see the 50-50 nature where mean, median, and mode is going to be equal. Okay, that is on the skewness. And now we are going into the second area of the nature of the dispersion of this data set, where we are going to learn this word kurtosis. Kurtosis, that is how we spell it, kurtosis. Okay. Now, previously, we are assuming, okay, fine, we are discussing about a particular data set where the peak, the height of the peak is pretty much in equal heights, pretty much in equal heights. So if you look at the positively skewed, negatively skewed, or symmetrical distribution, these peaks were at one particular area. Maybe let's say frequency is 50 or 40. Okay, fine. We did not discuss about the variability of the frequency of the mode, median, and mode at the central point. Now, assuming that I mean, we can have the discussion on kurtosis for for a negatively skewed or positively skewed distribution or a normal distribution. But here, what we are going to discuss is that, students, whether we can see the peaks frequency is going to be higher or lower. Whether we can look into the peaks frequency as a higher or lower. Why? This curvature nature of this distribution is going to tell you a lot more about the nature of the data set. If you could recall that cricketer's example I called some times ago, if that chap has played maybe 1 or 2 zeros and 1 or 2 hundreds, and if the majority is towards the 30s, 40s, and 45s, what can we conclude? We can conclude the fact that, okay, fine, at the next match also, that player will play on average close to 20s or 30s or 40s. Why do we need that again? To forecast. I mean, not to make a bet or to make a business call, but I mean, if you are running a business and let's say if you're producing something, if you're trying to plan your advertising budget to target a particular sales level, what do you need? You need to understand where my previously collected data set is going to take me. Where they are going to take me, and under the collected data set, what kind of decisions that I can make. Okay. So this data, if you can really, see, they are concentrated extremely to the center, extremely to the center. You may see maybe 1 or 2 data points on the left hand side and 2 or 3 data points on the right hand side, but 30s, 40s or 50s number of data points on the center. Now there we can identify, okay, compared to this normal nature, let me again highlight the fact that we are assuming some particular level, let's say 30s or 40s for this particular height. Normal. In compared to that height, if you can identify a significantly large, maybe let's say something like 120 to 200 kind of height. Don't take this as a scale. I'm just trying to plug some numbers and give you an understanding. So once you see these two height differences, now in this instance, students, we can identify, okay, fine, there is a greater concentration of data towards the central point compared to a normal instance. In such instances, we call this kurtosis nature as a leptokurtic curve. Leptokurtic curve. Opposite side, flip side, the height is extremely low, something like 5 to 10. We call it as a platykurtic curve. Okay. I mean, how can you, derive into conclusion by just by looking at the nature? Okay, fine. All these are bell-shaped curves, but what kind of decisions that we can make? If you look into a centralized data set versus a normal data set versus something like this platykurtic data set. Now here you can now this is a probability game. It's a normal. It's a normal curve, and your value can be anywhere over here. And this is a very vague game of probability, platykurtic. You have no idea absolutely where your next value is going to be. It's almost like a flat curve. But in an instance like this leptokurtic nature, you can jolly well define a very small bandwidth like this and demarcate, okay, fine. My greatest probability for the next value is going to be between this A to B. This A to B. So that range is extremely narrow. So you can make a very fine call. A good example of this leptokurtic curvature will be something like a yogurt factory. Yogurt factory bringing up their yogurt production. So we all know that although maybe the height is around 75 grams per small cup, the companies, they try to optimize it to make sure that 75 grams are there. So they have to be ethical. But what about the machines? Can the machines think and exactly drop 75 grams? No, those machines have to be calibrated. Calibration is not very easy. So that depending on the calibration, depending on the weather, the machine operator, the weight of the yogurt and the ingredients, the machine will sometimes produce maybe 76 or 74, likewise different ways. So that's why for a food production packaging, they always mention that could be plus or minus maybe 1% or 2% likewise. But for those operators to define this range of A's and B's, now let's say this is going to be 75 grams. This B is going to be something like 75.3 grams. And this is going to be something like 74.7 grams. So if that is the case, so they can be still happy, okay, fine, this is extremely close to 75 grams. And if you see your data being moving here and there with more higher frequencies, if this is converting into something like a normal distribution, one can say obviously, okay, fine, there's something wrong with this machine. It is giving me 73s and 78s, different values. Okay, so there are likewise there are practical instances of all these nature of curves being applied in businesses and different domains. So that's all. Seldom I have seen much questions on these natures of the skewnesses and kurtosies, but then again, for a good MCQ question, two-mark question, you can be tested on the nature of the height of the data set for the left or right skewness of the data set. Okay, so this is the second indicator we discuss and we learn that the kurtosis. We can categorically identify leptokurtic, mesokurtic, and platykurtic, three instances. Mesokurtic is the I mean, like in the previous instances of skewness discussion, like we have the symmetrical distribution. Mesokurtic instance is the symmetrical nature of the height. It's not very high, it's not very low. It's the yardstick for us to compute whether, sorry, for us to conclude whether it's a leptokurtic instance or a platykurtic instance. So one could argue, okay, fine. For a given data set, we can only land in one of these three instances. So how can you have the comparison? And there are standardization party, as in where you can convert the any distribution into a standard normal distribution, and then find an equivalent set of values, which we will be discussing at the latter classes. Okay. Any questions so far on skewness and kurtosis? I'm sure these are pretty straightforward theoretical areas. Okay, great. Moving on. Now, from this point, this lecture is going to be getting a bit complicated and very interesting. Now, this is where we are going to introduce two variables, students. Now, be very careful. This is not x variable and its frequency anymore. It's not x variable and its frequency, but it's x variable and a corresponding y variable. It's x variable and a corresponding y variable. Let me demarcate it at the very beginning. So far, what we have discussed is instances like you have a set of students in a class, 70 students. Let me try to draw it so that you can remember it clearly. You have 70 students. Okay. So far, what we have discussed, this class, what we have discussed is single variable x. What are those examples? Let's say heights, weights, likewise measurable single variables. Maybe this is in centimeters, this is in kilograms, likewise. Now, let's say there are 70 students, and then what are those bell-shaped curves and all? This is maybe, let's discuss one instance of weights, maybe 60 kilograms is going to be the average, and there are 13 students with 60 kilograms, 62 kilograms, something like 8 students, likewise. So this is all what we learned so far. Now, once you introduce two variables, what is going to happen? This entire, this classroom, this 70, it's going to be the same. It's going to be the same. Sorry. Absolutely, there is no difference into what we have discussed so far. But what is going to happen for these 70 students? Sorry. For these 70 students, for these same 70 students, now we are going to bring in two variables. Two variables. What are those? X and Y. Oh, the classic example that I can quote up is for the same student, for one particular student, there is going to be height and weight. Height will be demarcated with the variable of maybe h, weight may be demarcated with the variable of y. Height and weight. Now, for one particular student, how can you write it then? Height something like, let's say 160 centimeters, comma, weight as 60 kilograms. For another student, now all this time, jolly well, we were writing something like 2, 3, 4, 5, likewise. So it's not the case now. You have to write like this. Why? We are bringing in more than one variable. Next student, 161 centimeter, 58 kilograms. See, same student. two variables. Why do I call these as variables? These vary. These vary from one student to the next student. Okay, hope you are clear. And just that I want to dedicate this slide and carefully show you that from this point, the equations that we are going to learn will have the impact of two variables. So these variables, so despite the fact that for your easy understanding, I just demarcate that height and weight are two variables, but the variables that we are going to discuss under this particular jargon, we demarcate one particular variable as an independent variable. Independent variable. Okay. So typically we take x variable to be the independent variable. As in, we can move that variable independently, and with that movement, what is going to happen to the value of the second variable is height and weight. Likewise, there's another variable for the same person. That variable, we are going to call it as a dependent variable. Dependent variable. So there is going to be one independent variable and the dependent variable. How are these data is going to be paired? Like this height and weight example. For the same person, you can demarcate two values in hand. It's the same person, two values. Maybe let's say if there are another measurable things like income or number of hours that they are studying. Likewise, you can put up multiple variables for one single person. It's very difficult to plot things like hair color or eye color, because those are again qualitative variables, remember. So quantifiable variables typically can have multiple for one particular person, for another particular person, one item, likewise. Classic example would be for an intangible thing like a box. You have height, weight, and the depth. Yeah. So the thing that we are going to learn first as the variability indicator is called as a covariability. Covariability. Sahavichalatavi, if I'm not mistaken in Sinhala. Sahavichalatavi. Covariability. What's the broad idea? Covariability is that whether we can identify the independent variable's movement is going to have a similar positive, negative, or no relationship instance for the dependent variable. How can we demarcate? We have to do some exercises. Not the physical exercise. I think you have to plot the data set into maybe a scatter diagram, and then we can identify. That is not going to limit our discussion. We need to understand the numerical value for the covariability. We can't use a scatter diagram and then plot these and say, okay, fine, we can see a positive trend, negative trend. That's not going to be enough. We will try to understand and learn one or two equations to calculate the covariability. But first, let's try to understand our concept a little deeper. Taking you to the third point, we can identify the interrelationship between x and y by plotting the x data in horizontal axis. Now, this is how we are going to do it. By plotting the x data in horizontal axis and corresponding y data in vertical axis. It's going to be something like this. X in the horizontal axis and y in the vertical axis. Y in the vertical axis. Which once you do it, students, what is going to happen? Now for this, even for this height and weight, still you can call one as the independent and other as the dependent, and you can do the same exercises. That's all. So importantly, you put a 0 at the starting point, and then once you plot this data, you will sometimes see outlier data also. These outlier data. Once you plot this data, this may be the data set that you're left with. Now, can we come into any conclusion? Bit difficult, but you will see in a while, even for this kind of a two relationships, you can still derive numbers by using some equations. So why we typically try to use this scatter diagram is by to just to eyeball it, just to eyesight it and understand whether we can see any relationships. The relationships can be of three natures: positive, negative, and no relationship. That's what I have highlighted here. Could be positive, could be negative, or no. We will learn each and every of these three. Now, once you assume that all these graphs that I'm discussing from here in onwards, x-axis is your independent variable and y-axis is your dependent variable. So what I have drawn previously is something like this. Your data is scattered a little bit further. You can't find a perfect relationship. If I'm being asked to draw something like a best fitting line, I would do something like this, but I'm not very sure because my data is scattered a little further. Look into this second instance. I can use my highlighter and comfortably draw a line. My comfortability or the relationships level is a bit more higher compared to the previous one. But now compare this third instance. Third instance where you can perfectly use a ruler and cut all these scatter points and draw a graph. What are these three instances? We call it as a perfect positive relationship, strong positive relationship, and weak positive relationship. What's the common word in all this language? The positive. Positive, positive, positive. What do you mean positive? How come? I mean, how did I say it's positive? It's simply because of the fact that when your independent variable is increasing, try to get this thing into your mind very strongly because this is a starting point of a lot of arguments also. When your independent variable x is increasing, how do you how do you call that x is increasing? Is simply by take the sorry. Let me draw it again. Sorry, let me try to clear it. When you do a x-axis drawing like this, starting with here 0. What do you mean x is increasing? Is we are always discussing with the assumption that your x value is going to move from here to the next point like this is 7, this is 14, this is 21. Likewise, it is moving from 0 to the positive side. Now this is what you call it x is increasing. X is increasing. In this graph, what is the x is increasing means? It means we are discussing these data points to the next data points, likewise. Okay. When x is increasing, we are going to observe what is going to happen to the corresponding y variable. Easy as that. What is going to happen to the corresponding y variable? What has happened? Now, look into a couple of values like this versus this. Hope you can see my red highlighting. This value versus this particular value. What has happened? Let's say this is x1 and y1, and this is x2 and y2. In example data, x1, y1, something like 5 and 3. X2, y2 could be like 50 and 70. I just plot some fictional data points. Okay. What has happened? X has increased from 7, 14, 13. I told you at the beginning, from 7 to 14 to 13 increase. So what do you mean by x is increasing in this particular two data points? 5 to 50. X has increased from 5 to 50. What has happened to y? Y has also increased from 3 to 70. 3 to 70. Y has also increased. So that's how you demarcate whether positivity can be noted. When X is increasing, if you can see your next values has also increased, then you can obviously call it as a positive relationship. Positive relationship. Now, what are these three instances in that case? Okay, fine, we understand it is positive, but what are these other words? These perfect, strong, and weak. Now, these are, students, nothing but some instances where you can note this positivity. If if it is perfect, you can find always, always for the next x value, the y value is higher. The next x value, y value is higher. It's like a straight line, like a straight line. What do you mean by the strong? Majority of the case, maybe 75 to 80 to 90% of the cases, you can see the value is increasing slowly. But some, maybe one or two instances, you may see that relationship is breaking. Still, you call it as a strong, positive correlate relationship. Sorry, not relationship, that's a different value. Strong, positive relationship. And the last part is weak positive relationship. What's this weakness compared to these previous two? You can see your scatter graph is going here and there. It's not a perfectly nicely aligned scatter graph. See, the values are here, likewise. Now compare these two values. Compare these two values and try to come to a conclusion. When x is increasing, what has happened? Y has remained same. Isn't that so? Small x value, y. Another small, larger x value, same y. See, now it's a bit difficult for you to come into a conclusion with this nature, saying that your relationship could be strong or perfect. Such instances, but still, when you look at the big picture, such instances, still you can demarcate, okay, fine, these relationships is going to be in the positive nature. How do you conclude? You have to draw a best fitting line, like what I did at the very beginning. Best fitting line. Best fitting line. You could recall that at our childhood days, we used to do it by measuring these distances to the perpendicular nature and try to minimize these gaps and draw the line. There's one particular theory area which we will learn in a little while in the sixth area. There is a simple linear regression. That is exactly what we are doing. We take a set of data points and then we calculate these lengths, and we will try to find the optimum point where the summation of these are going to be have the minimum value. What do you mean? In such instances, these heights are going to be giving the minimum instances. Obviously, we will discuss with more detail over there. We call it a regression exercise, and obviously this relationship that we are learning under covariability will be quantified and we can find a best fitting line. This line's equation can be demarcated. Y equals mx plus c is the typical form. We can find this m and c and identify a particular equation for this scattered nature. Okay. Great. We deviate a little further, but then again, quickly we'll try to find what's the flip side, the negative relationship. Obviously, we don't have to spend much more time. You can see the exact what we learned so far, like in the positive skewed, negative skewed. Here under covariability also, students, you can see the exact three instances what we learned so far under the negative relationship. What do you call the negative relationship? That's all what we have to demarcate here. When your x is increasing, see, x is increasing. Now I'm not going to draw again. X is increasing. What is going to happen to the y? See, y is dropping, not increasing anymore. Y is dropping. This is x may be 5 and y may be 50. This is x is 50, y is 5 now. X is 5, y is 50, and this is x is maybe 70, y is 5. See, your x is increasing and y is coming down. X is increasing and y is coming down. So in such instances, students, we can identify this negative relationship, negative relationship, negative relationship. That means when your independent variable increases, your dependent variable goes down to the other side. Similarly, your perfect, strong, and weak instances are going to remain same with our previous argument on the positive relationship. So you can find perfect negative relationship, strong negative relationship, and weak negative relationship. Don't forget the fact that these are no longer heights of the single variable, but we are now discussing about x variable and y variables, two variables. Two variables moving hand in hand. Now, for the covariability measures, okay, we learn what these instances are, positive, negative, and now we are going to measure those into an indicator so that we can identify, compare, and come into conclusion for a particular data set. The first indicator, there are a couple of indicators we are going to learn. Covariance is the first one, and correlation coefficient is the second one. Covariance and correlation coefficient. Covariance is the first indicator, and it is a measure of how much two variables vary together, how much. So you may typically assume, okay, fine, there may be, okay, positivity, negativity, and zero kind of an instance, but not really. Under covariance, what we are going to learn is that how strong or how weak by comparing a number on the particular two variables. Now, typically, for the sample and for the population, we have two instances. Like in our any argument of sample and population, the only difference is that n versus n minus 1 for the sample. So you could recall the variance equation. Xi minus x bar divided by n. Variance. If it is a standard deviation, you take the bracket n or n minus 1. Yeah. The same argument, but here no longer xi minus x bar to the square, but rather now we have two variables. So how do we calculate the covariance is by first, for one particular value, we take the xi minus x bar. And for the same item, we take the y value also. Yi minus y bar. And then we divide it by the n or n minus 1. But I'm sure you must be thinking, okay, fine, x bar we understood so far. Where is this y bar coming from? Y bar or this other yi's and xi's, where they are coming from? Let me try to clarify it over here. Now, students, for a casual conversation, I'm just trying to take a data set of x's and y's. Now we know so far, okay, fine. We take the scatter diagram, try to understand where the data is heading, and then come into a conclusion. Let me try to plot up some values so that you can understand it clearly. 1, 3. This is 4. Try to align this a little so it's easy. This is 5. And this is 6. About this is 1, 2, 3, This one also I can give 4. Let me manipulate this a little bit and call it as 5. And the last one is maybe 7. Did I miss any data points? No. Okay. Now, this is a typical scatter diagram with values in it. Okay. So for this covariance, students, now what am I trying to do? I'm trying to figure out this golden relationship between whether I can find a best fitting line like this. But for this, to first understand the covariability, I need to calculate these individual x bars and y bars. So what are these x bars and y bars? If I try to, take these values into some kind of a plane for our discussion purpose, this is 1, comma 2. How do we write this? It is x comma y always. X comma y. So this is 1 comma 2. This is 3 comma 1. About this point, 3 comma 5. This one, 4 comma 3. 5 comma 5. 6, 4 and 6, 7. Okay. Now, if I try to isolate these x values, 1s, 3s, 3, 4, 5, 6 and 6. If I just take it out, forget the fact that I'm looking at a 2 variable instance, and if I just take it out for the discussion sake, 1, 3, 3, 4, 5, 6 and 6. If I do the same thing, this is the x set. If I do the same thing for the corresponding y variables, 2, 1, 5, 3, 5, 4 and 7. Now students, you can understand fine, okay, despite the fact that we had 2 variables, this is, you can still calculate x bar. Let me just put a fictional x bar value like 4. Yeah, y bar, something like 5. Now these are the values that I have taken before in the equation, x bar and y bar, for our equation on covariance, x bar and y bar. Yeah. So let me try to take the same this thing and show you how do you take this x bar and y bar into the picture. How do you do it? You take the individual x value, let's say 1 minus 4, and the corresponding y value 2 minus 5 plus, I'm taking the next value, this one, 3 minus 4 multiplied by 1 minus 5 plus, likewise. Why do I take this multiplication? Because the equation says so. The equation has the covariance calculated as the corresponding x variable minus the x bar into y variable into, sorry, minus y bar. So that's why students, I always have this 4s here and these 5s here. Xi minus x bar, xi minus x bar multiplied by yi minus y bar. Okay. So once I have all these, covariance, once I have all this summation, and then divide it by n or n minus 1 depending on whether I'm looking at the sample or population. Since most of the time I'm looking at a sample, let me just straightforwardly take it as n minus 1. Then for this answer, we are getting the value for covariability. Value for covariability. That's why I have defined here where x bar is equal to xi divided by n and yi divided by yeah, let me try to answer this question. Yeah, Ladita, actually, now this is a very fictional value. I didn't calculate y bar. If you calculate y bar, what's the correct value? 2 plus 1 plus 5 plus 3 plus 5 plus 4 plus 7 and divide by 7. Yeah, it's going to be something like 3.8. Yeah. So the correct value, just for the discussion sake only, I just took 5 here. This is perfectly has to be something like 3.8. For x bar, is my fictional value is going to be aligned with 4. Yes, yes. Correct, correct. Sorry about that. I understand your confusion now. So I just hypothetically put 4 here, but it's a correct value. But for y bar, it is going to be 3.8 precisely. So if I quickly update my equation here, so instead of 5, I have to minus it by 3.8. Huh? Sorry about the confusion. 3.8. So going to be 1 minus 3.8. Likewise, you take all these values. You take all these values, take the minus of xi to x bar, yi to y bar, take the summation, divide by n minus 1, and there you can calculate the covariability, covariance, covariance. It's going to be an answer. It could be any number, but there again, once you calculate it, you can compare two or more data sets, whether your covariability is higher or lower, or whether you can see a stronger or a weaker. But it is not going to be enough for us to conclude whether it's going to be stronger or weaker just by looking at the covariance. Just by looking at the covariance. Why? By computing the covariance, you can't really say it's a positive, positive, negative. Fine, it's a concludable thing. You can easily come into an answer. But how do you really compare this with some sort of a scale? You can't. Why? Because of the fact that it is, I mean, this computation, this xi minus x bar multiplied by yi minus y bar divided by n minus 1 is obviously going to come into an absolute number. Absolute number. So just by looking at absolute number, students, you can't comment on the uh, comparison sake. You can't comment on whether it's a strong, weak, or no relationship instance. For that, we need to require one more additional covariability indicator, which we call as the correlation coefficient, which we call as the correlation coefficient. Let me try to recall it one more time. We have learned a few more few more diverse words in this short span, starting from variance, standard deviation. Then we came here for the covariance. What are we trying to learn? Covariability. Covariability. Okay. So for the covariance, you can get an absolute answer. Absolute answer. Not a relative number, not a Likert scale number like negative or 0 or from negative 100 to positive 100. No, nothing like that. Still, for this covariance, you may be able to demarcate it's a positive or a negative. That's fine. But once you calculate the correlation coefficient, students, now this indicator is the final answer we are looking at. This indicator is the final answer we are looking at, where this is going to tell you, fine, okay, this particular data set, these x's and y's, these independent variables and these dependent variables, whether am I looking at a strong, moderate, or a no relationship or weak relationship, for this particular given data set. For this data set. Let me take you through the text. This is a measure of strength of the linear relationship between two variables. Now, important thing which I couldn't like really discuss with you is that this particular word, my apologies again, this linear relationship, I need to take a little time and discuss with you about these types of different relationships. Now, students, in statistics and in mathematics, there can be different relationships between two variables. Linear relationship is the easiest one, something like this, linear. But what about something like this? Something like this. Something like this. Maybe something like this. These are also relationships. It doesn't necessarily have to stop your assumption by saying that if there are no relationships, there are no relationships. That statement is wrong. Let me repeat it. If there are no if there are no linear relationships, there are no absolute relationships. If I say it like that, that statement is wrong. What I implied here is that this is the thing which we discussed so far. But that doesn't really say for the two variables x's and y's, there will not be any other relationship. What about this? It's like a quadratic equation. Something like y equals ax square plus bx plus c. It's another form with a minimum and a maximum. This could be something like y equals ex, y equals log x. Likewise, this is y equals sine x. So in mathematics and statistics students, there could be many more relationships. For one particular x variable, there can be different y variables, but that doesn't necessarily say that it is going to be limiting our linear relationships. So that's why here in students, I have categorically mentioned that this correlation coefficient is going to only measure the strength of the linear relationship. So one could argue, okay, fine. All the other discussion that we had so far on two variables, categorically on the covariability, discussing on the scatter diagrams, although despite the fact that for x and y's, if there are no relationship instances, if I take you here, see, weak negative relationships or no relationships, something like you draw a scatter diagram and you can't find any relationship. Important thing, we are looking at a linear relationship only for this discussion. But if you take the advanced mathematics course, there can be many more different relationship types, but which we can't cover up depending on the breadth of this course. Okay, having said that, so this linear relationship between two variables will be given by this correlation coefficient as the indicator, and importantly, this indicator, unlike the other ones, we will learn in a while that this will come with a scale. We will learn how these values will be falling into the scale and how to demarcate. But first, let's try to learn how to calculate this. And let me demarcate this equation is as one of the most difficult equation in our curriculum to remember. There are two forms for you to keep in mind. Keep in mind. The first form is the easier one. It comes with a theoretical background, but the second form is absolutely an expansion or a practical application of the calculation part of the correlation coefficient. In the interest of time and in the interest of the course curriculum, we don't really intend to demarcate and show you how you can calculate, how you can come into this equation form, but you can do a bit of a googling and use YouTube and try to dig a little deeper if you are interested. For our discussion, first we'll try to understand what the correlation coefficient is going to give you. Now students, previously we have calculated this beautiful value covariance. We are going to start with the same covariance here. See, same covariance. If I just try to plot it here, it's going to be xi minus x bar to yi minus y bar divided by this entire thing divided by n minus 1 or n depending on your data set. With this top, we are going to deduct it by the variance of x variable xi minus x bar to the square divided by n minus 1 to the root, in fact variance, and then once you take the root, what do you call it as the standard deviation. It's going to be yi minus y bar square divided by n minus 1. Now this is the bigger or the expanded form of this equation. Covariance between x's and y divided by variance multiplied by variance of these individual variables of x and y. X and y. Now you may assume, okay, fine, this particular equation is a form of this expansion, that how it may have come into this particular form. It is, and absolutely correct. So you have the flexibility depending on the exam question, whether you have been given into the argument of calculating covariance first and then calculate correlation coefficient. I would really recall that calculating correlation coefficient with this top equation form is the easiest one and the most logical thing to remember. But the bottom equation, of course, I'm sorry, I really can't give you an explanation as to how to remember. But then again, if you really look into the detailing part, your n into sigma xy minus sigma x and minus sigma y is the only uniform part, and these two parts what you can see here on the bottom, similar to the variance x and variance y, it has a similar form. Pardon me of this small typo. This has to be to the power 2, not zoom this equation a little bit. Yeah, now it's correct. Not that it is multiplied by 2. So you have this form of n or n minus 1 depending on your data set into sigma xy minus sigma x minus sigma y divided by this root n sigma x square. Now what is this? What is this? Individual x values, you square them and then only you take the total. Individual x values, you square them, then only you take the total. What about these values? This is nothing but sigma x and sigma y. You take the sigmas and that particular sigma total. Let's say you have 1, 2, 3, 4, 5, like that, and then your sigma x will be something like maybe 120 or 130. That particular 120 or 130 is square. That's the only difference between this sigma x square versus sigma x's square. Okay, that's all we have to really highlight here on this equation of correlation coefficient. To sum up, we discussed two formations, two methods to calculate the RXY or the correlation coefficient. This is called as RXY, simple R or capital R. XY, once you put it into multiplication form, x into y, that gives you an indication, okay, we are talking about a correlation coefficient. Correlation coefficient. Okay. So, yeah, this is on the computation part. Now, the explanation part. Once you do this calculation, students, once you calculate this RXY, I mean, look into the ingredients that you're feeding into this equation. You're putting up a some sort of a xi minus x bar onto the top, multiplied by yi minus y bar, and onto the bottom. So you have this xi minus x bar squares. Then you are taking. Let me use the pointer. Talking about here, this part, xi minus x bar multiplied by yi minus y bar. Forget about this n minus 1 for the moment. Once you have this xi minus x bar to the square, and then once you take the square root, eventually you are left with something like 1xi minus x bar to the square. Here, this side also, yi minus y bar, one element will be left with. So 1xi minus x bar and on the bottom, similar value. 1 yi minus y bar on the bottom, similar value. Once you do this crossing off and do the computation, students, you will eventually understand that unlike you calculate this covariance equation, where you will be effectively left with a number. Number as in you have the xi minus x bar, yi minus y bar divided by n minus 1. So this is going to give you a number something like 23, negative 5, something like that. But once you do this crossing off, you will understand that effectively you will left with a number from 0 to 1. From 0 to 1. With negative side also, depending on whether you are looking at a positive correlation or a negative correlation. So that's the beauty of this correlation coefficient of Rxy and its measures. So that's why I told you at the beginning, for our answer of this comparability or the strength, we need to understand, okay, there has to be one additional indicator for us to calculate the strength of the indicator that we just calculated, correlation coefficient, that is the Rxy. So typically students, from -1 to +1 is the range that you will find the Rxy no matter how you calculate the equation correctly. At the exam, that's important indicator for you to remember. If you calculate Rxy and you demarcate a value like 2.5, obviously your value is wrong. You have to quickly redo the calculation again. Eventually, you will have to left with a number like something like 0.7, 0.91 negative. Now these are good values. Why? -1 to +1 is the range for the correlation coefficient. So now there are some norms or soft rules. If it is close to +1, there is a strong positive correlation. If it is +1, it's a perfect positive. Yeah? But seldom you can find a perfect positive correlation. That's a straight line. If you see a straight line, obviously students, once you plot it into the scatter diagram, you will not come to the calculation of correlation coefficient. Why? From the eyesight of it, you can understand, okay, there is a straight line. No, not a problem. But once you do a scatter diagram, once you see the scatterness of data, only you are coming here to find a relationship. Isn't that so? So that's why typically we don't discuss the +1 instance, but rather close to +1 or close to -1 is the area that we are going to start our discussion. If R is close to +1, it's a strong positive. Sorry. If R is close to 0.5, call it a moderately positive. If R is close to 0 from either side, there is a weak positive. Or on the negative side, weak negative. So on the other side, flip hand side, the explanations are exactly same. -1, strong negative, -0.5, moderately negative, likewise. If R is 0, again, now that is the instance we can perfectly demarcate. There is no any correlation. Is that the correct wording? No. No any linear correlation. I repeat, and that doesn't really give you an indication that no, absolutely no relationship kind of a conclusion is wrong. No any linear correlation. Okay. Right. I think we can try out a couple of exam questions. There are not more than 8 to 10 different exam questions in this area, but mostly we saw exam questions from part number 1. There are ample areas to be tested from the very basic theories. But nonetheless, there are questions, and I mean, there are complete 20-mark questions also coming into this picture, but maybe 10 or 15, but maybe 5 coming from a different area like charting or explanation. Still, it is stemming from the lesson number 3. To sum up our discussion, I put this summary slide so that your different doubts on this wording and their naming should be taken off. First, we learned variance for one single variable. Why did we learn variance? To understand how data are spread around the mean value. This blue text is what I have put it as my explanation, how data are spread around the mean value. That's why we calculate the variance. Simple as whether you have a x bar and variance s square will give you, okay, what sort of a range that my data is varying around, likewise. And then we calculate this coefficient of variation. It's the s divided by x bar. Plenty of calculations we did last week. It is going to give you a relative dispersion. You used to compare distributions. S1 minus x bar versus S2 minus x2 bar. Kind of a comparison. That's what we learned so far. So here at this part, what we have learned is covariance first. This is to derive 3 positive, negative, or no relationship instances. Positive, negative, or no relationship. I told you that you may get values like zeros, 23, negative 200, likewise. But this is not going to be sufficient at all. It's not going to be sufficient at all. So you need to calculate this last indicator, that is the correlation coefficient. This is going to quantify the strength of the relationship. Rxy is going to tell you from -1 to +1 to 0 where your data point is going to lie on. Whether you can demarcate as a strong positive, moderately positive, or weak relationship. Okay, that brings the end to our discussion, and unfortunately I'm left with not more than 10-15 minutes, but then again I think this is more than sufficient for us to discuss few exam questions. I can leave the rest to you to try it at home. Are there any more questions before we quickly try to yeah, I think Adit is correct on my previously miscalculated y is equal to 5. Sorry about that. Yeah, do another example on coefficient as in, are you discussing about correlation coefficient or the last equation, of course, this one I believe, correlation coefficient. Fine. Now this is where students, we are trying to understand the strength of the two variables, whether they are moving at a perfectly positive relationship, perfectly negative relationship, strong or weak. You could recall that once you look into these scatter graphs. Let me erase them and show you. Once you look into these scatter graphs, you may recall that, okay, fine, by just eyesighting, you can jolly well come to conclusions saying that, okay, this is a perfectly positive, weak positive, but this is not going to be sufficient, isn't that so? In statistics and mathematics, we can't really be relying on a graph, but rather we have to come to an equation to understand this strength. So if you find a straight line like this, where you can take your ruler and perfectly draw a line like this, there's absolutely no point going from here onwards. Rather, you can close your discussion saying that it's a perfect. The word perfect is being used over there. But for all the other instances, these strong and weak instances and no instances, we can't really eyeball it and stop our discussion. So that's why first we can calculate the covariance between the two variables and understand whether it's a positive, negative, or a zero kind of a relationship, and conclude. And once you have that, still you can't take it into one kind of a Likert scale, a scale to universally compare the correlation, the variability of two variables, and x's and y's, and then demarcate your conclusion saying that it's a strong, moderate, or a weak relationship. For that only, we need to calculate this correlation coefficient of Rxy, this equation. How do you calculate it? Simply by the logical way is that you divide the covariance of these two variables by the standard deviations of x and y. Covariance by the standard deviation of x and y. And the expanded version, if you plot the numbers of these individual values of covariance, standard deviation of x, standard deviation of y, this is what is going to be looks like. Covariance xi minus x bar, yi minus y bar. That is what we learned at the previous slide. The variance is what we see in here. When you take the roots, it's the standard deviation. So this there are two forms of this equation, students. You have to keep in mind. The first form is this correlation is going to be equal to covariance divided by the two standard deviations, and you can plot the numbers. And the second form is a derivation which is coming from this same argument, but it is put it in a different way. Sometimes students, you may find this equation little bit funny, but when you look into a data set only, you will understand fine. Okay, you don't really have to calculate this xi minus x bars, but rather you may have x values, y values, x into y, x square, y square. In such instances, you can forget about the covariance and variance and standard deviation and calculate the correlation coefficient by using this lengthier equation. Okay, I believe that's good enough for a bit of explanation on the last equation. Shall we try a couple of exam questions and you will understand? Yeah, great. You'll understand how it is being tested in two instances. Bear me with the time, students. There are important questions, but at least let's try to cover up quick 3 to 4 questions. And categorically, let me try to show you how that last equation is used in two different forms. There are two questions. I have the written answers also, so let's quickly try to discuss. Okay. Now, this is 2019 September question paper. This is question number 7. This is a 2-mark question. So sorry, I don't have the part number 6 above. The question is asking. Okay. Look at here. Question is asking data given in the question number 6 above. Only missing piece of the question number 6, which we don't have in question number 7, is the number of observations. That's number of observations. Okay. So I've taken it here as n is equal to 30 from my question paper. So for our discussion, let's take you to the question and try to understand what need to be calculated. A linear relationship is observed. See the word linear. A linear relationship is observed between daily average daytime temperature X and consumption of electricity in Kandy in June 2019. So average daytime temperature, if it is high, maybe the consumption of electricity could be higher if they're using maybe air conditioning, something like that. But there could be a vice versa discussion also. If the daytime temperature is lower, maybe they're burning some furnaces to make their heating. Likewise, there could be different relationships. So one is trying to find that relationship, and for that part, they have taken up this portion of this equation and going to give you and going to ask you to calculate the sample covariance between x and y variable. So it's a straightforward calculation per se. How do you calculate the covariance? The equation is xi minus x bar I minus phi bar. You take the sigma of this entire thing, and since it is sample n minus 1. Yeah. So this portion is given. So this is going to be 2800 divided by 29. I'm bringing in this n is equal to 30 from the previous question, so that This is the answer that you need to look for, 96.55. See, I told you for covariance, you may get numbers like 90, 10, -3, likewise. But still, from that absolute number, students, you can't really give a conclusion. So with this, what kind of a conclusion that you can say? It's a positive. If the daytime temperature is high, consumption of electricity is also higher. That's all you can conclude from here, just by looking at this 96.55. Okay. The answer should be close to 96.55 or 96.6 is also correct if you round it up to 1 decimal point. Okay. This is 19 March, elective question number 2. Again, this question is going to discuss about some electricity consumption and daytime average temperature. We'll read through the question carefully and try to grasp what is being displayed here. Sorry. Great. Following data indicates monthly consumption of electricity in Y variable and the monthly daytime average temperature in X variable. Now, don't get carried away. Sometimes this X and Y, the examiner doesn't really have to, stick into himself or herself, say that X or Y is going to be the only way to indicate the independent and dependent variables. So be careful. Sometimes he may name Y as the independent variable. Yeah. In a city in 2018. So you seem to be having monthly data from 1 to 12, and this X seems to be what? The average daytime temperature in degrees of Celsius. And Y seems to be the gigawatt hours electricity consumption. What can you just eyeball it and see? If the temperature is lower, you may see low electricity consumption, and if the temperature is a bit higher, you can see some higher electricity consumption. So that's all what we can demarcate from now. All right, moving on. The first two parts, I think I've taken it out since it is not relevant here. And we are looking at part number 3 and part number 4. Following observations were made on the monthly data of X and Y. See, now the examiner is giving you, okay, this is sigma X, this is sigma Y. This is yi minus y bar to the square, portion of the variation equation, right? So those are given. So this is for the covariance. Parts are given, and n is given as 12, which we see in the 12-month example. That's fine. What is being questioned here? If you really look into the question, it's only asking, first part is the average temperature in 2017. It's one of the most brilliant questions I've ever seen in this paper. It's simply because of the fact that you've been given, a pretty heap of data inputs and asking for the average. How do you calculate the average? Is by simply taking the fraction of these two, isn't that so? What is X stands for is the average monthly average temperature. Asking for the average temperature in 2017 and its standard deviation. So the first part is going to be nothing but xi divided by n is going to be 27.58 is my answer. 331, where is this coming from? 331 is here. It's the sigma x, it's given. N is also given. Am I going to take n minus 1 here? No. For average, we take all the data points. Only for the standard deviation of the population and sample only, we are going to take n minus 1. So for the standard deviation, see, I've taken the sample standard deviation. Standard deviation, students, I have taken n minus 1. And this ingredient, this top part is also given in the equation. See, xi minus x bar to the square. If I write it here for you to quickly see it, standard deviation is equal xi minus x bar to the square divided by n minus 1. If I take the root, that's the standard deviation. If I take the value without the root, that's the variance. So this portion is given students 163, and since it is a sample 11, I told you at the beginning, unless otherwise not mentioned as population, we always take the sample. My answer is 3.85. 3.85. For these two, you are getting full 5 marks. This is the average daytime temperature and its standard deviation. Yep. Complete part number 3. Part number 4. Using 2017 data, calculate the sample covariance and sample correlation coefficient. Now this is doing the justice for the time that you are leisurely spending on part number 3. And it doesn't stop there. It is also asking to interpret the value for the correlation coefficient. See, now for these 5 mark students, you have to work for maybe 10 marks kind of a effort. First, calculate the sample covariance. Now, the wording covariance is going to give you, okay, fine. It's going to be something like, yeah, it's going to be something like you take the xi minus xi minus x bar, then you have yi minus y bar. You take the sigma and divided by n minus 1. So this covariance can be calculated without an issue. And for us to compute the sample correlation coefficient, students, I can recall I told you that you can either use the logical equation method or you can use the expanded method. Both methods are correct. One thing is that you have to keep in mind of the equation of the expanded method. So here, since the examiner just calculated the sample covariance, is asked us to calculate, the easiest one would be to calculate these by standard deviation of x and standard deviation of y. Why? Just because that we calculated it here, and this part we calculated in part number 3. So I can plot these numbers easily. Only missing piece is I have to quickly calculate the standard deviation of y. So this is faster. Nonetheless, for the other portions, you have to do a lot of work to compute the sigma x, sigma x square, sigma y square. Those are not given. So this is, I would recall, as the only method that you can calculate the correlation coefficient here. Let me quickly share the answers and show you how I derived it here. Okay, for the first part, sample covariance, this is given as 1331. This portion of the equation is given as 1311. N minus 1 as 11. With that, we can conclude the sample covariance as 119.18. See, I told you that the values can be something like negative zeros and 119, but with this value 119, students, you can't interpret anything about this relationship between this daytime temperature and the electricity consumption. For that, we conclude our argument by calculating the correlation coefficient. See, this 119.18, easily we can plot it here. Standard deviation of x 3.85, we just calculated. That's also under control. Only thing which is missing is the standard deviation of y. If I quickly calculate that part, now luckily this sigma yi minus y bar, this 12,544, this is also given. So all what I have to do is this divided by 11, take the square root of it. And 33.77 is the standard deviation for y. So once I have that values, it's all about taking the calculator and plotting the numbers. 1119, 3.85, 33.77. And beautifully, I'm getting a strong positive correlation coefficient of 0.916. It's not perfect, right? If it is to be perfect, it has to be 1. But I recall for a perfect positive this thing, you don't really have to come here. You have to just plot the scatter diagram, and the scatter diagram will tell you itself that it's a 1. Perfect. So since it is close to point 0916, I can conclude this as a strong positive correlation. Yep. So you have to do a bit of a writing and do your elaboration. Interpreting as in, once you come to the Rxy is equal to 0.91, you have to tell that, okay, if I take X and Y like this, if I take X as my independent variable as the temperature and Y as my dependent variable as the electricity consumption, we can find a we can find a strong positive correlation between these two values. That means when the X values are increasing, you can find there is a 91% kind of a probability that Y values is also going to increase, okay? Or that correlation is 0.91. Likewise, you have to do a bit of a write-up and do your writing. Yep. So this is one particular form. If you could really bear with me for another couple of minutes, I can conclude the lesson just by showing you a different example of how it is been asked in the equation form. A quick MCQ: statistical analysis provides the following summary: average, dispersion, skewness, and kurtosis. Which of them are used to describe important characteristics of a distribution? See, average is the X bar. Dispersion is a broad word, but it includes many different indicators. Skewness and kurtosis is also all different indicators. So I could recall that the answer could be D for this one. All A, B, C, D. All these are summary measures, and these are important characteristics of distribution. This is 18 March, question number 4. Yeah, with this discussion, I'll try to close it up for the day. Look into the explanation, and we will try to find out. Question number 4, and 18 March. This is also elective question. And quickly, let me try to elaborate the case for you. X is the advertising expenditure. Try to zoom up a little bit. Yeah. X is the advertising expenditure, and Y is the number of new accounts opened in a particular bank. So what can you typically, express? I mean, at a broad daylight, come into conclusion. If the higher the advertising expenditure, the number of accounts are going to be opening is also going to be a bit more higher. See, advertising expenditure is 150 accounts. When it is being increased to 250, 350 accounts, likewise. But you may not see a perfect verdict here. First part, plot X and Y on a scatter diagram and using judgment. See, using judgment, just eyeball it and understand it and state whether there is a correlation between X and Y. Comment on relationship observed. State possible reasons for the large variations in the number of new accounts opened monthly. So if you do your math correctly, you have to get a scatter diagram like this. There are different scatter points are there, and you can draw a befitting line of taking the advertising expenditure and number of accounts open into these two axes. But for the arguments on the variation, you can argue, okay, fine. It could be seasonality, maybe month of April and all, due to this seasonal offers, there could be many accounts opening. Maybe due to the expenditure higher nature on month of December. Likewise, you may not see much account openings, rather money withdrawals. Likewise, you can argue some possible reasons. Yeah, but the focus of this question is not the part number 1, part number 2, which we learned just a moment ago. Using the values given below, calculate the correlation coefficient Rxy between X and Y. Interpret the value of the correlation coefficient R. Now see what is being given here, students. So unlike the previous instances of where you can take the what do you call this covariance and divided by standard deviation, now here you have to use this form of the equation. See, some these indicators are directly given. Some of these indicators, now I think most of these indicators are given, except the fact that n is equal to 12. You have to take it from January to December. That count is 12. Yeah. So the form of the equation and its application is going to be something like this. Rxy is going to be equal to n sigma xy minus sigma x sigma y, and this one part root of n sigma x square minus sigma x square. Now this is what you have to be only be careful of when to take the square values and to square it yourself. See the application. N is 12. This is taken directly from the paper. Sigma x given 3000, sigma y given 3750. That's one aspect. N is 12. This sigma x square is given. Now this part, just focus here. See, sigma x is 3000. Sigma x is 3000, but here you have to take the sigma x and then square that particular value. Here also sigma y is given, you have to square that value. Yeah. Now this is a good classic example in 2018 March. Yeah, 18 March paper. The question, the examiner has asked you to sorry, calculate the correlation coefficient between these two independent and dependent variables by using the longer expanded equation. So all these ingredients are given, simply focusing on the this particular equation form. And if you do your math correctly, try to plot the numbers and get the number yourself. You should get 0.93 as the correlation coefficient between these two variables. Yep. So 0.93, I don't have to spend much time here. You know how to do your explanation. If the higher the number of money that is spent on advertising, the higher the number of accounts being opened. It's having a strong positive correlation. The rest of the questions, students, let me leave it up to you in the interest of time. I really wish if I had a little bit more time to discuss, but then again, if you just eyeball these things, again, you have a table, maybe months, and then profit after tax and rain seems to be the two variables. And depending on the formation of the equation is given to you, you can guess, okay, fine. What's the expectation of the examiner to calculate this correlation coefficient? The other explanations are pretty much similar. Another question that you can attempt 16 September. This is mainly on trying to calculate the skewness of the data based on the conclusion of your graphing. You can conclude whether this data is skewed, this data is symmetrical to one particular end or otherwise. 16 March, it's a typical good question on a scatter diagram. Identify the relationship, demarcating 30 days average temperature versus the electricity consumption. If there are exceptions, you have to explain why it is not the case. And then see again sigma x, sigma y, sigma x square. Two ingredients are given here, and then you can calculate the correlation coefficient. Last one, what are your conclusion when the correlation coefficient becomes +1? See, it's a perfect. So this scatters is going to be not a scatter, but a perfectly straight line. Good question. Try to give it a shot. And few more MCQs and minor questions for you to try it at home. Okay. So those who are keen to try these questions on your home, and when you try it, and if you hit an obstacle, you can always email me and get a clarification. But I really implore that the more questions that you try, it will going to be very much easier when you are close to the examination. Sorry about the extra 10-12 minutes. If at all you have any questions, I can still be at your disposal and discuss. I think only tricky part on the today's discussion is all summarized in this last summary slide, which I just showed you. Try to build up your own note on this particular slide. the way that you understand the summary of this entire discussion. Try to plot into a few more these things and equations of our previous learnings so that it will be very much comfortable. I mean, don't be, if I just quickly try to show you my revision slides also. There are, yeah, there are some revision slides which I'll be sharing it with you momentarily. Uh, if I quickly take up a particular page. Yeah, this is how your note should be. Uh, I mean, on your own, try to come up with this summary of these numerical descriptive measures, mean, median, and mode, what they are, what to be used in such instances, the nature of these curves, skewness, kurtosis, and lastly, covariability, positive, negative. And this is the slide that I insisted. The covariance, correlation coefficient, how to interpret these equations and what to be kept in mind. Okay, if there are no any other questions, I can wind up for the day. And about the classes, I'll let you know. Hopefully, I prefer to have maybe 2 or 3 extra 2-hour classes rather. I mean, delivering this online methodology is a bit tough rather since I don't have much feedback from you. So rather, if I continue it for 3 hours, I might lose the momentum and try to be distracted. So shall we try to have maybe 3 or 4 extra classes in that case? I hope you can bear that with me. The the new lecture schedule will be informed to you by the IPSL staff. Our usual classes will continue on the Sunday afternoons. Okay. All right, ladies and gentlemen, then let me wind up for the day. You have a good evening and you all stay safe.